Okay, we're going to go ahead and finish up section 7.3 now. Just showing you some more examples of solving equations. And so here's another one. Suppose that we want to solve sine of 3 theta plus pi over 18 equal 1. Okay, well, let's see here. Sine of what angle would give me 1? Well, I know sine of pi over 2 is 1. Right, that's one of my major angles there. Sine of pi over 2 is 1. Now, I don't have just plain old theta here. I've got an angle of 3 theta plus pi over 18. Okay, so I'd want to set that angle equal to pi over 2, but then use the periodic factor where I'm adding increments of 2 pi radians. So, if I then solve for theta, pi over 2 minus pi over 18 divided by 3 would give me 4 pi over 27, and then 2 pi k divided by 3 is going to be added to 4 pi over 27. And so now I'm going to select values of k to see if there's any, to gather up all the values that would be on the interval of 0 to 2 pi. Remember that for these problems, you're assuming that you're working on the interval of 0 to 2 pi unless you're told otherwise. So if k is 0, you're going to have 4 pi over 27 plus 0 is 4 pi over 27. That's going to be an answer. If k is 1, 4 pi over 27 plus 2 pi over 3. Well, 2 pi over 3, that'd be the same as 18 pi over 27. Plus 4 pi over 27 gives you 22 pi over 27. That is going to be on the interval of 0 to 2 pi, so that will also be an answer. If k is 2, then let's see here. We're going to have 4 pi over 27 plus 4 pi over 3. Well, 4 pi over 3, that is the same as 36 pi over 27. Add 4 pi over 27 to that, and you get 40 pi over 27. That's on the interval 0 to 2 pi, so that will also be a solution. If k is 3, the 3's will cancel here, and you're looking at 4 pi over 27 plus 2 pi. 2 pi is the same as 54 pi over 27. Plus 4 pi over 27 gives you 58 pi over 27. That is now bigger than 2 pi, so you're going to disregard that number. Any k value bigger than 3 is going to mean that you're now producing a theta value that is bigger than 2 pi, so we don't have to check any further here. It looks like these 3 angles would be the 3 solutions to the problem. Now, in these problems, make sure that you're getting all the solutions. Okay, we have to make sure that we're using the periodic factor. I see more than I should where students will only get like a 1 answer and there's like 3 answers. They didn't use the periodic factor, when they should have. So be careful about that. Okay, here's another one. Let's solve the equation 2 cosine squared theta plus cosine theta minus 1 equals 0. Now this is a trig equation, obviously, because of the cosine theta terms that we see. But we could also call this a quadratic equation, right? This is quadratic in form because I've got a squared term, a linear term, and a constant all added together to give 0 on the right. Now we've seen problems like this before where we have something that resembles a quadratic and we can use a u substitution. If I let u be cosine theta and I square both sides, u squared would be cosine squared theta, and so I'm going to have 2 u squared leading off plus cosine theta, that's what I'm calling u, okay, minus 1 equals 0. And yeah, so by making this substitution here, you can see more clear that we had a quadratic going on. It was just kind of hidden in disguise a little bit. So knowing that I've got a quadratic means that, of course, the next thing would be to factor. This is going to factor nicely. And when I set the factors equal to 0 and solve for u is equal to 1/2 or u is equal to -1. Now, I don't care what u is. U is just a temporary thing to help me see that I had a quadratic going on here. I'm solving for theta, right? So at this point, you'd want to substitute back. U is cosine theta. And so you'll have cosine theta equal 1/2 or cosine theta equal -1. Cosine theta is adjacent over hypotenuse, so when I set up my triangle here, the adjacent side is 1, the hypotenuse is 2, the opposite side would be √3. we're working with a 60-degree angle there, and so pi over 3 radians would be one answer. Now, if you flip this triangle over into quadrant 4, that's going to affect the opposite side, which we don't care about for cosine theta, right? Cosine theta is adjacent over hypotenuse. And so cosine of 5 pi over 3, that would also be 1/2. Now, I don't want either of these triangles to be in quadrants 2 or 3, because then the adjacent side would be a -1, and I need to be a +1. So let's go on to this other equation here. Cosine theta equal -1 means that theta would be pi, and that's going to be the only value here on the interval that is 0 to 2 pi. So these three numbers are going to be my three answers on the interval of 0 to 2 pi. Okay, here's another example of something that's quadratic in form. I want to solve for theta. Now the plan here would be to start by getting everything in terms of either sines or cosines. The fact that I've got two sine theta terms means why don't we just go ahead and get everything in terms of sine theta rather than cosine theta. Now I know that sine squared theta plus cosine squared theta equals 1. That's one of my Pythagorean identities, and that's an important identity. I had mentioned in chapter 6 when we looked at that stuff that would be one that I'd want students to memorize. Be sure that you know all three of the Pythagorean identities. Those are important and they will come up a lot. So if sine squared theta plus cosine squared theta equal 1, then cosine squared theta would be equal to 1 minus sine squared theta. And if I replace the cosine squared theta term by 1 minus sine squared theta, then now everything is in terms of sine theta. Collect your like terms, and if I get everything onto the other side here, so that leading squared term is a positive, then I'm looking at 2 sine squared theta minus sine theta minus 1 equals 0. That's a trig equation, obviously, because of the sine theta terms, but it's also quadratic. Right? I've got a squared term, a linear term, and a constant added together to give me a 0 on the right. So, just like in the other problem, I want to set up a u substitution. U is going to be equal to sine theta. If you square both sides in that, u squared would be sine squared theta. And so I'm going to have 2u squared leading off minus sine theta, so we're calling u, minus 1 equals 0. And again, I can see more clear now that I actually had a quadratic going on. It was just kind of hidden in disguise a little bit. So this one is going to factor nicely. Here's the factors. And when you set the factors equal to 0, you're getting u equal -1/2 or u equal 1. Substitute back, u is sine theta. And so now I'm looking at sine theta equal -1/2 or sine theta equal 1. I've got to solve these two. Okay, sine theta is opposite over hypotenuse. The opposite side is -1. The hypotenuse is 2. That's going to mean I'll be in quadrant 3. The adjacent side would be -√3 then. And the angle that we'd be talking about there would be 7 pi over 6. This is a 30, 60, 90 right triangle. If I were to flip this triangle over into quadrant 4, that would affect the adjacent side, which I don't care about for sine theta. Right? Sine theta is opposite over hypotenuse. And so I'd still have sine theta equal -1/2 there. And we'd be looking at a 11 pi over 6 angle then. I don't want either of these triangles to be in quadrants 1 or 2 because then the opposite side would be a +1 and I need that to be a -1 here. So I think these are going to be the only two angles on the interval 0 to 2 pi that we'll be using. And then sine of theta equal 1. Well, sine of pi over 2 is 1. And that's going to be the only major angle on the interval 0 to 2 pi that we're going to be using. So these three numbers would be the three solutions to the equation there. Okay, now there's a couple of these that are quadratic in form in the book. Okay, of course you want to be using a u substitution in the process of solving. Okay, here's another example. I want to again solve for theta, and I'm going to start by using the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. Well, that means that cosine squared theta would be equal to 1 minus sine squared theta. So if I use that identity, then now everything is in terms of sine theta. And here would be my quadratic in form. And if I let u be sine theta, u squared minus u plus 1 would be equal to 0. Helps me see, you know, that it actually was a quadratic going on there. This one won't factor nicely for us, so I'd want to use the quadratic formula. And I'm getting u equal 1 plus or minus the square root of negative 3 all over 2. Now, we're not doing anything with I or imaginary numbers when we're solving, right? It's all about the real solutions for theta. So this equation would have no real solutions to it. Okay, here's another one. Sine theta plus cosine theta equal 1. If I begin by squaring both sides, then foiling out the left, sine theta plus cosine theta times another sine theta plus cosine theta is going to give me sine squared theta plus 2 sine theta cosine theta plus cosine squared theta equal 1. Now sine squared theta plus cosine squared theta is 1. And if I subtract 1 from both sides, then I'm looking at the middle term here, 2 sine theta cosine theta equals 0. Divide by 2 on both sides, and that gives me sine theta times cosine theta equals 0. Now the nice thing about squaring this out and then foiling is that now I'm looking at multiplying rather than adding, okay, and I can separate these factors, sine theta equals 0 and cosine theta equals 0. So when does sine theta equal 0? Well, sine theta equals 0 when theta is 0, pi, 2 pi, 3 pi, right? I'm working on the interval 0 to 2 pi, but I'm not including 2 pi for these problems. So theta would have to be 0 and pi for the interval that we're working on. Okay, when does cosine theta equal 0? Well, cosine theta equals 0 when theta is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. These are going to be the only two numbers on the interval 0 to 2 pi that we're going to want. Now, although it's not obvious here in this problem, we'd want to check for extraneous solutions because we squared both sides. Now, when you're working with radicals, like if you're solving an equation that has a square root, usually you're going to be squaring both sides and, you know, somewhere in the process. And the fact that you're squaring both sides is the reason why you're checking for extraneous solutions. It is not because there's a square root there. It is because you squared both sides. Okay, so I want to check my solutions in this problem since I was squaring both sides. When we do that now, so if theta is 0, sine of 0 is 0, cosine of 0 is 1, 0 plus 1 is 1, that's true. If theta is pi, sine of pi is 0, cosine of pi is negative 1, 0 minus 1 is not 1, it's negative 1, so pi would be extraneous. Okay. How about pi over 2? Well, sine of pi over 2 is 1, cosine of pi over 2 is 0, 1 plus 0 is 1, that's true. And then if theta is 3 pi over 2, sine of 3 pi over 2 is negative 1, cosine of 3 pi over 2 is 0, negative 1 plus 0 is not 1, it's negative 1, so 3 pi over 2 would be extraneous. Looks like 0 and pi over 2 would be the only solutions to that equation. Okay, at the end of this section, they've got a few problems where you're using a calculator. Again, most of these are going to be with no calculator. I mentioned that a couple times in the previous videos. Keep that in mind when you're working through the problems here. The idea is that you want to be able to solve without a calculator, since that's what you're going to be expected to do in calculus, and that's what you would be expected to do in an ordinary trig class. let's look at a few where we actually are using a calculator. We're still in the interval 0 to 2 pi. Okay, and so in this example, what if I want to solve the equation cosine theta equal 0.6? Well, if I take cosine inverse of both sides, cosine inverse of 0.6, and of course make sure that you're in radian mode. I am in radian mode there. But cosine inverse of 0.6 is 0.93. Okay, so here's 0.93. That's going to be one solution. Now, I want to make sure I'm getting all the solutions on the interval 0 to 2 pi. Some students will stop right here and say it's roughly 0.93, and then go to the next problem. Don't do that. Cosine theta is positive if you're in quadrant 1, since everything is positive in quadrant 1, and also in quadrant 4, since the adjacent side would still be a positive. Okay, cosine theta would be a negative if you're in quadrants 2 and 3, since the adjacent side would be a negative. So I need to look at the possibility of an angle existing in quadrant 4 where cosine theta is 0.6. Well, one complete revolution around the center is 2 pi radians. And using symmetry here, if I take 2 pi minus 0.93, I'm getting 5.35. That would be another answer that I'd want to give. Again, anything in quadrants 2 or 3 I don't want, because then the adjacent side would be a negative. Okay, here's one more example. Similar deal, solve the equation sine theta equal negative 1/5. If you begin by taking sine inverse of both sides, then we'll have sine inverse of negative 1/5 is negative 0.2. Okay. Now, I've crossed that out. Why did I do that? Well, I'm on the interval 0 to 2 pi, right? So I don't want any negative numbers. But I want to be still getting any solutions that would be on the interval 0 to 2 pi. So here's what would have been the angle negative 0.2. One complete revolution around the circle would be 2 pi radians. And so if I take 2 pi radians minus 0.2, that would give me 6.08 radians. Okay, so 6.08 radians would be the same radial line as negative 0.2 radians. It's just I don't want a negative number in my answer here. Now, if this triangle, which is not one of my common triangles, is flipped over into quadrant 3, then that's going to affect the adjacent side, which I don't care about for sine of an angle, right? Sine of an angle is opposite over hypotenuse, and the opposite side would still be a negative. So I'd want to look at that possibility. Now, here's the pi axis. Okay, and if I add 0.2 radians to pi, pi is roughly 3.14, right? So that'll give me 3.34 radians then, and these would be my only two answers. I don't want to look at any triangles in quadrants 1 or 2, because then the opposite side would be a positive, and I need that to be a negative. So again, one of the key things, make sure that you're getting all the solutions in these problems here. All right, I had another problem at the end of this section. I was only going to do this if there was some time to spare in class. In the past years, unfortunately, I haven't had time to do that problem, although I have done that one before. But I'm going to omit that, and we'll call it good here for this section. So the homework in section 7.3 is on page 478. Be sure to look at those problems for me.